right, and so now before I completely close down and erase this particular definition, it's all due to the fact that this definition of our derivative of a function at a given point f of x, and this is pretty much the only definition given out, and the very first definition given out in terms of what a derivative is at a given point, and also it gives a way of how to find the derivative f prime at a. And so if we're now looking closer into this derivative, this definition of how we can find a derivative, then it heavily involves the idea of taking limits. And so now for that reason, due to that reason, so this definition of any derivative to any function at a given point a is famously being referred to as, so yes, it's formally a definition of any derivative, but a lot of time many instructors and students would eventually also fall into this routine, this habit of referring to this definition as it's the limit definition. Right? So the definition we're seeing right here is called the limit definition of assuming that we now all know what f prime of a means. So f with a prime symbol, it's one symbol, but means that this is the derivative of the function f of some function f at a given value x equals a. But this entire definition here that I put in a box right here is being referred very commonly in these days as the limit definition of f prime of a, or of the derivative of a function f at a given value a. Okay, and so at this point we are ready for pushing our understanding into a couple of examples right here. So I need some time to erase the board. And so to continue from the earlier examples right here in this particular lecture right here, then we're now at example 2. But after we have learned what a derivative is, as far as seeing the derivative, the definition, the limit definition, then here I call that example 2, and I'm going to start out by saying in this example 2, we're going to have a function. So I'm going to say let f of x, some function f of x, be, how about, let's try with the f of x equals x cubed function. So x cubed function here is similar with f of x equals x squared that we have done earlier. Basically, x cubed and x squared here has one common thing, that they are powers. These two are all powers of x. Our function we're about to work with in example 2 right here is a power 3 function that the function that we mostly focus on throughout our earlier part of this lecture was the power 2. So it was a square function or a quadratic. But so now let's put a pause on the square function. Now in this particular example, let's say we want to consider f of x equals x cubed. So after that given function, let's say we want to find f prime of a. So here's the general instruction of the example. We want to find the derivative. So f prime here, now start getting comfortable to this symbol over here, but f with a prime symbol means I want the derivative or the slope of the tangent line at some given a. And so a here, I am about to give it out here. So how about at x equals 2. Okay, so f prime of a generally means we want, again, the derivative of the function f of x. Here's our f of x. F of x equals x cubed, and this symbol is indicating that we want to find throughout the entire example 2, we want to find the derivative of the function at given a, at given x value, x equals a. And so now specifically for part A, I am looking for the derivative of this function at x equals 2. So now I have to emphasize this 2 right here is a right there. Okay, so that 2 right there is a. All right, so to get started into this problem, once again, the famous limit definition, and that's pretty much the only definition for what it means by being a derivative. And so here, since we already had, starting in part A, we already had a given specific A value, then I am having my legal right. We can have our legitimate reason to write f prime now no longer generally as an f prime of A, but here we can specifically say this is f prime. Our problem, example 2A, is f prime at 2. Okay, and so find f prime at 2. This is going to give me as a starting point. So I need anybody, as you're progressing with this video over here, as we're making progress, and make sure you had your notes that you have taken with the earlier part of this lecture and look back at the formula that I erased already. But the limit formula the limit definition of this derivative says what we need as a starting point. And really, I really want my aim, my goal for this, after this video lecture, is anyone after viewing this video lecture is comfortable with setting up that starting point, that famous starting point. So the starting point here needs the function f. I don't need to know what the function is yet, but we always start out with, we have to know the function f with input 2 plus h. See, this is our A right here. So I need to produce f at 2 plus h. And then I'm going to subtract f at 2. So note how A here is our given value, just like when I was explaining about that finding slope of the tangent line. So here I'm going to repeat those A values right here in my difference quotient. And then we divide by h. So that famous difference quotient is here. But now the limit definition is telling us that we need to apply the limit operation. So now I'm going to take the limit of this difference quotient as we are letting h getting close to 0. Okay, so this is the famous starting point for any derivative problem. All right, and so now I am going to move to the other board and get our problem worked out. And then maybe let me also put part of the other board there so we can still see what was the original steps here. So the next step now leads us to, and so pretty much we have at this point it's heavily based on our algebra skills that we need to manipulate with the expression. So the function was simply the x cubed function. So f of x equals x cubed. So now with our starting difference quotient is indicating we need f of 2 plus h. So the function itself is x cubed. So now I'm going to say 2 plus h, the inputs now being cubed, minus f at 2. So f of 2 is simply just 2 cubed. So this is how I set up my difference in the numerator. And the denominator is just h. So this is how I start developing further my difference quotient, provided my function now is kicking in. Okay, and so in the next step here, or maybe I should save that. I should save this next step for the next line right here. Okay, and so now at this point I have a high recommendation. This 2 plus h right here, well, definitely we have to follow it out. So we can think of this little scratch work here. We can think of this as 2 plus h times 2 plus h times 2 plus h again. And I was short of space here, so let me write it smaller. So 2 plus h all cubed is the same as 2 plus h as a factor times with 2 plus h as a factor and times with the third factor of 2 plus h. So all three factors of 2 plus h multiplied together. That's what this 2 plus h all in parentheses cube means. So this is the easiest way. I'm not saying that it's the fastest way to get your work foiled out, but this is always the safest way and easiest way to understand. And so yes, if you don't remember all of your algebra skills from the past right here, this is always a safe start. And then we're going to start foiling things out one by one. Now, additionally, we can use if any of you can remember from your past algebra course that we've seen the idea of the Pascal triangle allowed me not to mention too much about that, but the Pascal triangle helps you to bring out the coefficient of this is a binomial, and then at the high powers. So I can just remind everyone about the Pascal triangle, but allow me not to explain too much about this, or maybe I will give a separate explanation of what this Pascal triangle does. But we have here a Pascal triangle, and so this is power 0, this is power 1, this is power 2, and this is power 3. And this helps you to expand, to FOIL out, and these are the final coefficients of that when you apply into a binomial being raised to a power like this. But then if anyone still remember this, it's a good plus. It gets your work done a little faster, but otherwise you're not required in any way. You're not required to know this Pascal triangle. And if you want to see some other review stuff about that, maybe I'll have some other videos outside of this particular lecture right there. But so back at this particular 2 plus h all cubed for here, after FOIL, this is what we get. So we have 8, which is 2 cubed. Okay, and I'm going to add. Okay, so excuse me for the jumping around, but so I have 8 plus 12h plus, and now I'm going to have reduce my coefficient to 6h squared and plus h cubed. Once again, if anyone having a question for me of how I got to that from FOILing this out, then yes, pause the video, take your time to FOIL out the 2 plus h all cubed equals 2 plus h times 2 plus h times 2 plus h, and do that carefully and combine like terms carefully. I am sure you will land into this. Okay, and take your time when you're learning any math skill right there. And so now this takes care or replace our first term in the numerator of our difference quotient right there. But we still have more in our difference quotient. So now I'm going to subtract 2 cubed is 8. And then I have my denominator being pretty much left the same there. And so the problem was supposed to be a limit problem, but we haven't done any limits, so I'm leaving the limits operation attached there. So this is our step right after successfully getting the function kicked in. All right, but now at this point, more algebra is waiting for us ahead. We can subtract, we can cancel the common opposite terms here. So after canceling out the 8 away, now my fraction reduced down, my quotient here reduced to something a lot simpler. We're looking at 12h plus 6h squared plus h cubed over h. Okay, and from that step to this step right here, it's simply just the algebra. And so I haven't done any limits, so I'm going to permanently keep that limit symbols the same there. Because the reason we're still keeping the limits is because remind yourself ultimately again that we're taking limits of a quotient, and any of these steps so far, if we roughly plug in the limit h equals 0, the limit 0 into our h variables right here, we are going to end up with a 0 over 0. Okay, by using the limit laws immediately into any of these steps. And so it's not safe yet. And check with the steps again. If we're substituting h, the whole point, I now start using the term substitute quite oftenly here, but that's because all due to the fact that we already had the limit laws allowed us to work on a limits problem like substituting it. But so now it's dangerous that when we're substituting in right here, then we're still looking at 0 over 0. And anyone experienced enough in viewing this video, anyone viewing this video is experienced enough to tell that this is still 0 over 0. Trust your own math skill at this point. And so that means we need to move on further with the algebra before we can successfully use the limit laws right here for plugging it. And so now I see that I have a common factor h right here, throughout my 3 terms in the numerator. And so I am going to factor out h, and inside of my parentheses, now what I have remains here is 12 plus 6h plus, I need a little more space, so h squared here. Okay, so each term here reduce the power of h by 1, and then we're dividing that by h right there. And we still have not done any limits work yet, so I'm leaving that limit symbol the same. But now the usefulness of doing this now is we can, I mean, that gives, that opens a door for the next step. So now we can cancel the h away. All right, and so in my next step, we're looking at our expression, our difference quotient there reduces down to 12 plus 6h plus h squared. Okay, and now I'm throwing in the limits symbol. We're taking limits of this problem as h is getting close to 0. And now anyone can quickly see that we are now in a safe zone. And safe zone, in a sense, that safe zone means that if we apply the limit laws, the basic limit laws, which allows us to work like we are plugging in the value h equals 0 into our expression here, we will get a safe answer, a finite answer. So now, limit laws say the limit of the first term being a constant function, so it's going to be 12. Limit law says 6 times h is going to give me, but when h goes to 0, so that middle term is going to become just 0. And then the third term here, as h goes to 0, h squared is going to approach 0 as well. So our final answer now, summing up all these three values, we're looking at 12 as our final answer. Okay, so once again, what a long process, but hopefully anyone viewing this video didn't lose track of what we were doing. Remind yourself, after so much limit work, but our ultimate goal was to find the derivative. The entire reason that we produced all that limit work for us was because we ultimately, or originally, was finding f prime at 2. So this f prime at 2, now we have an answer. So that here, our final conclusion, f prime at 2 here equals 12. Okay, so that's our answer. Okay, or we can say that the derivative of this function, f of x equals x cubed, its derivative at 2. The derivative of the function at 2 equals 12. What is the function? It's this function that we're working with. Okay, and so I did part A. Now the same example I am going to put on part B, but my intention here, part B, I'm putting here same function, but I'm intending for viewers to work on your own and find your own answer. I'm only going to write down the answer. All right, so I want to find f prime at A again. Pretty much the same kind of problem, but now part B. Let's say at, how about x equals 1. So now I've learned this style from one of my respected professors when I was in graduate school. FYT right here is intended for you to try, for your own trying right here. That means viewers, please pause the video and carry through the steps to get the problem, to find out the answer on your own. So basically, as a starting point, I want to find f prime at A, but A here is given to be 1. So that means we are finding the value of f prime at 1. And I can quickly help you with the starting step again. So this is limit of f of 1 plus h, okay, minus f of 1 divided by h, and let h go to 0. All right, so that's about the best I can help you with, but I'm going to be waiting for your own answer. All right, so hopefully you've had some answer and worked through your steps here, but after lots of algebra steps, we came down to the answer being 3. Okay, and so in other words, our final answer for this particular function, again, f of x equals x cubed, I'm saying that f prime, the derivative of f, of our current f at 1, that derivative value equals 3. Okay. And that's how it's done. Okay, so let's continue working on more derivative problems, but now I'm gonna call those example 3 here. Okay, so leave me some time to erase the board. All right, so here we go at our example 3 right here. So this time I'm going to give even shorter example description right here. I'm just simply going to say let f of x, and you know what? I changed my mind. Why don't we, I just want viewer to be more flexible in terms of functions name. We don't always have to use f of x. It could be g of x or h of x. It's a name of the function. We can name our function whatever. So at this point, I'm feeling like I've been using way too much f of x. So let's stay with g of x. How's that? Okay, so g of x here, let's say we had our function here being x squared minus 2x. Okay, so that's the only description we've had. Okay, and so now I'm going to get starting with my question A here is I'm going to start, I want to evaluate, and that's the only next piece of information regarding the general description of our problem. But so once we have the function defined, let's evaluate. Now, how about g prime at 1? Okay, so we keep getting shorter and shorter in terms of the amount of wording. Okay, so let's take a moment to understand what we are being asked to do. We had our function previously given right here. Our function is defined to be, well, our function g of x is x squared minus 2x, meaning we square every input, then we subtract 2 times the input. Pretty ultra basic stuff, right? And so, but now question A is asking us, in connecting this piece of information with the ending part of our general instruction about the example, then we're looking for evaluating, we want to evaluate our g prime, our derivative of g at x equals 1 right here. So you see how powerful it is to use symbolic expressions there. Okay, and so now once again, the limit definition of g prime of 1 is the only way we can get through and get to our final answer. So as a setting up step right here, just a starting, and that's also the setup step right here. G prime at 1 is famously defined, right? And now let's let that limit definition kick in again. The function now is switched to f of x, so I have to use g. Now our input value here is 1, and so that means we're going to have to use g at 1 plus h minus g at 1. Okay, so this is, I'm slowly constructing my difference quotient over h. Okay, and we refer to this as a limit definition because we heavily rely on the limits concept right here. So after setting up the difference quotient, we have to put the limits here, indicating that at the end we have to treat the problem as a limit problem, even though it was massive amount of algebra that we've seen throughout all of our examples. And by the way, no matter how far we have gone, I just need to, at some point, I will constantly remind viewers that derivatives at g prime at 1, f prime at 1, g prime at 2, but all in the end, these are meant to be the slope of the tangent line. The slope of the tangent line, if we can see the graph of this function, then this is the slope of the tangent line at x equals 1. So any derivative to any function is the slope of the tangent line to that function at the specific given point right here. So never lose your ultimate purpose. Okay, so now we call this the derivative of g prime at 1. So the next step can be done by, okay, so our g prime, g itself is x squared minus 2x. So with this, right after this setup right here, g at 1 plus h means we are going to substitute 1 plus h into every x value of our function. So 1 plus h all squared, but now our function has 2 terms. So we have one more term, and everything I'm talking about right now is just how we substitute the expression 1 plus h into our current function, which has 2 terms. So 1 plus h all squared minus 2 times 1 plus h. You can see up to this point I've done math for a long time, but I always use parentheses very carefully here, especially anytime I'm substituting value into my I'm substituting value or an expression into my input variable of any function. And that's the reason why I have 1 plus h in parentheses square minus 2 times in parentheses 1 plus h. So all this here replace my g of 1 plus h. So that only took care of our first term in the difference quotient, and especially the numerator of that difference quotient. But now we need to subtract. So now g1 says, and once again I'm doing input square. So the input now is 1 minus 2 times the input being 1. So all that next part here inside of my next pair of brackets, this is indicating that we're looking at g of 1. Okay, and so g of 1 plus h minus g of 1 over h. And we need to treat the problem ultimately as a limits problem. We're going to start taking limit as h goes to 0. So right from here, if we're looking at this problem as, if we're trying to approach this problem by immediately letting limit laws come in and treat the problem as plugging in h value equals 0, then we're going to fail. We're going to end up immediately with 0 over 0. And that's the reason why we need to continue using the algebra to get some good amount of simplification for this expression. So let me go to the other board and let's continue on. All right, so in my next step, and carrying on from the previous step right there, then, and it's also a good idea if I can show part of the other board, part of our screen here. So from the previous step, and now the x plus h all squared can be rewritten as 1 plus 2h plus h squared. Okay, and once again, you can always pause the video to reveal your own skills about how you can FOIL out a perfect square or a perfect cube like in the previous example. Minus 2 times 1 plus h. This term came out from that previous term, and it pretty much stays the same. Okay, and we are now square brackets and minus, and then all these numerical values, we can quickly calculate them. So, or we can leave them same. So minus 1, but I'm moving on with two little steps combined together. So minus 1, but then plus, due to a sign change here with minus a negative inside. And so plus 2, and you have your choice to go ahead and combine like terms for those. So I'm holding on to the next step. Okay, over h, as we get limits to 0. Okay, and so the next step is going to be, we're going to take the parentheses out, and notice here we have a negative sign again in front of a parentheses. So distributing that minus 2, be careful with your sign change right there. So here I'm looking at the first group of parentheses. After taking out the parentheses, we're looking at just 1 plus 2h plus h squared. But that middle big term right there, after taking out distributing that minus 2, we're looking at minus 2h, sign change. And now no more parentheses, and then minus 1 plus 2. And so I left these two terms without combining for a reason. So now we can see that we have pretty good amount of opposite terms to be cancelled away. So 1 cancel with negative 1, minus 2 cancel with 2, and by the way, I forgot to put the h in the denominator, but that's easy to fix. And all that work there is waiting for our limits work. So let's check again. Even when we got to that step, it's still not safe, and you can tell me that. Pause the video and check for yourself. If we treat this step right here, if we can treat that step by simply applying the limit laws, it's not going to work. It's still going to give you a 0 over 0. And that's the reason why we need to continue simplifying the expression to come down to this step. Okay? But even with this step right here, let's clean up the terms. Now just clean up the terms. After simplifying all that there, let's see what we have. 2h plus h squared minus 2h. I actually didn't notice I also had two other opposite terms to cancel out right there. Okay. And so now that means I only have h squared right over h here. All of a sudden the expression became really short. Then letting h come to 0. And so now with that work right here, then now I can, and right at this point, let's check again. Is it safe yet? And safe, I mean, is it safe to use the limit laws? Sadly, it's not yet, because here, if we're substituting the value h equals 0 into our expression, we're still going to end up with a 0 over a 0. So it's not safe yet, but let's cancel out, let's simplify even further. Let's cancel out the h common factor here. So we consequently ended up with h, one simple term, that's simplest function on earth. So limit as h goes to 0. Okay, and now this will all become just 0. Okay, and so our final answer here, and after a lot of steps, basically just focusing on the limit works right here, then we might have lost track of what we were doing. But now remind yourself, our problem was to find, let me create a little space here for myself to write here, but our problem was to find g prime at 1. And then let me put up the other screen again. We were setting this up as a general expression, as a general starting setup for any limit, for any derivative problem. And then we start working through and walking through the steps here, and now we arrive at our final answer. So final conclusion here is g prime at 1, the derivative of our function g at x equals 1 equals 0. Okay, and so that is our that is our answer to this part A of our example 3. Okay, and so again, I want my viewers to have some opportunity to work alongside with me. So same example, let's not close it down yet. I am going to produce a part B. So let's evaluate, and we are still on the same function. Let's evaluate g prime at -1. But so now I'm intending this problem to be as an FYT here. And FYT means for your own trying. Okay, and so maybe I can help with just a little bit starting step right here, but famously to find g prime at -1, and remind yourself g prime at -1 means we want to find the derivative value of g at -1. So a is here, g prime means the derivative value. And so the famous limit definition comes back in again. Our function is g, but now we're going to need -1 as our a right here, a plus h. So we always go g at a plus h minus g at -1, because this is g of a, and then divided by h. This is our famous difference quotient right there. And we need to take the limit operation after we successfully set it up and simplify the difference quotient right here. Okay, and so go ahead and pause the video, take your steps, and let's compare answer at the end. All right, so after hopefully having your own steps right there, then final answer should come down to -4. Okay, and so our final conclusion here says that means g prime at -1, ultimately that was our original goal, has answer -4, or the slope of the tangent line tangent to this function, this curve of the function g of x equals x squared minus 2x, that the slope of the tangent line, I keep making that interchangeable understanding, so hopefully it stays in your mind right here about what the derivative is for. So g prime at -1, or the slope of the tangent line to that graph right here, to that curve at x equals -1 is -4. Okay, and so now let's get on with another example which gives any one of you the more experience in terms of working with our derivative here. All right, so now let's look at example 4 here. Once again, quite similar to example 3 we have done previously, but I'm going to switch to a different function. So let's look at I'm going to call that h of x this time. Okay, so purposely want anyone viewing my video to be flexible about how we name our function, and but the concepts remains exactly the same. That generality, the limit definition of our derivative stays exactly the same. So h of x here equals, how about just square root of x? Okay, and so once we have defined our function, let's evaluate in the example I've had in mind here is, let's evaluate how about h prime at 4. Okay, so h prime at 4. So our function is h of x, and here the problem is asking us to evaluate h prime at 4, which means let's evaluate the value of its derivative, the derivative of h at x equals 4. So that's what we are instructed to do. And so that famous starting step, again, that famous starting setup, again, we need to set up our limits definition on with that difference quotient. And so at the starting, h prime at 4 is famously defined as we have to create our difference quotient. So this time, since we switch our function's name to h of x, and so I'm going to use in my difference quotient h of my a value given is here, so it's h of 4 plus h. See, I realized my mistake a little bit by using the function's name here, which makes it a little confusing. Not too badly, but it could be a little confusing between these two h right here. Okay, but this is the name of the function, and this is the, how about let's do this. Let's change this to capital H. Okay, function's name is just a function's name. So I'm looking at capital H right here. And here is capital H. Okay, so capital H. Let's get it clear right here. But capital H is our function's name, and h is just that temporary variable that we always use. And when you get flexible enough, you can also use any other variable's name for that h as well. So now capital H of 4 plus h minus capital H at 4. So this is our difference quotient right here being set up over h. Okay, and we need to be taking limit as h goes to 0. Okay, and so now our function capital H is being defined as a square root function. Now we're looking at the actual setup where we have our function applied in. So with our function here, then we're looking at square root of 4 plus h minus square root of 4. Our function is a square root function. So that's why we're having that set up, and we're dividing that by h. Okay, and we are now going to take limit as h goes to 0. Okay, and so now I am going to move to my other board, and let's work out the next step. Well, right here at this step, the reason we have to work out the next step, once again, is because anyone at this point of your learning, you should be experienced enough to kind of tell ahead that if we directly substitute h equals 0 into the places of h right here, because we're using the limit laws immediately, it's not going to work out, because it's going to immediately give you a 0 over 0. Okay, so we don't even need scratch work paper to do that. We can just quickly and mentally tell, and so that's the reason why immediately using limit laws here is not going to work out. We need to use some algebra to simplify down that expression so that we can bring our expression into a safe zone. Okay, so into the other board right there. So now our next step now, and allow me again to bring that first step in some part of our board here. Okay, so with our function being currently written as a square root of 4 plus h minus the square root of 4 here over h. And this is a limit problem, but I haven't done anything to that yet. So now it's once again it's back to the algebra skill of how we handle. I have pointed out in my earlier video lectures that I see this as a difference and two separate terms. So even though it's pretty fancy looking here, square root of 4 plus h, but in the end, right around that minus sign, there are two terms. There's a square root of 4 plus h is one term, and square root of 4 is another term. And so the trick I'm going to be doing here, I am going to multiply with the, and this is quite a famous trick here, and my own favorite trick as well. But I am going to multiply with the conjugates of this. So here I'm going to multiply with 4 plus h, and I mistakenly wrote as 4h. So 4 plus h, okay, plus square root of 4. And that's what conjugate means. Conjugate means the exact same two terms, same exact two terms, but they switch the sign between them. The rule of algebra said anytime we multiply or anytime we multiply an expression to the numerator of a quotient, we need to make sure we multiply that exact same expression to the denominator as well. So that means that same conjugate right there, I must multiply to the denominator. Okay? It's just the rule of algebra. And it makes sense that way because we cannot out of nowhere just multiply things by something else. So if we decide to multiply anything to that, we have to cancel that away. There has to be a way to undo things. And that's my philosophy in terms of seeing that kind of action right there. But so now let's put things together. So the usefulness thing about multiplying the conjugate, and it's a pretty famous trick because as we have seen that before, multiplying two conjugate expression like this is going to run into the difference of two squares. So now I'm looking at square root of 4 plus h, that first term but now being squared. And then I said it earlier, just now I said it, difference of two squares. So there's a difference right there. And then the next term here, square root of 4 being inside a square. And anyone following along with this video is starting to find out how useful that is after in the next step right here, because here we have square, and squares are famous for canceling out with square roots. And by the way, so your denominator here, after bringing it all into one fraction, we're looking at h times square root of 4 plus h plus square root of 4. If anyone is being bothered with the square root of 4 being being left unchanged right here, or being without reduced, you can take your time reducing that. I just decide to do that at the last step, so you have your own freedom on that. Okay, and we need to take limits as h goes to 0. And so now, in my next step, I am going to produce, and just like I said earlier, any square operation is famous for canceling out or undoing the square root operation. So now square canceling out with that square root, my first term becomes simply just 4 plus h and no more square. Okay, trust me, people are so afraid of square root. And so thankfully, I was once afraid of square root too, but thankfully there's a square operation that can undo square root away. And anytime we are seeing an expression being inside a square root, it's dreadful experience. But now thankfully having square, we can get our expression out and throw the square root away. And so now, same way, square root of 4, I didn't even bother reducing it. Anyone, if you like to reduce it, you can reduce. But now square root of 4, square root, cancel with square, I leave back that 4 right here. So I didn't have to do too much work. So my denominator here becomes h, and I'm just leaving that the same there, times 4 plus h inside square root plus square root of 4. If you want to reduce that, so do it. But At this point, we can see that we have the two opposite terms here, 4 and negative 4, that can be nicely canceled out. And don't forget, this is not, we still haven't done any limits problem yet. Okay, and so after successfully canceling out of the two opposite terms there, let's see what our next expression is going to turn into. So we have h divided by h times square root of 4 plus h plus square root of 4, okay, and getting limits to getting h to 0. Right. So now, at this point, let's check again. It's still not safe yet to apply directly the limit laws, because when we apply limit laws, we're going to have a 0 over 0 again. Okay, but just one more step, and the victory will be right around the corner here. H cancel with that h due to common factor in both numerator and denominator. And so now, after canceling the h away, our numerator becomes simply just 1, and our denominator becomes a square root of 4 plus h plus, and now feel free, and I'm going to also reduce my square root of 4 right there. That's 2, easy enough. And now we're letting limits as h goes to 0. Okay, and now in the next step right here, at this point, let's check. We are actually now safe to proceed into applying the limit laws right here. And the limit laws now will allow us to work like we are substituting h equals 0 into our expression. And so now, with the limit laws being used in here, we're looking at 1 in the numerator and divided by a square root of 4 plus 0, because when h goes to 0, that term goes to 0, and plus a 2 outside right there. Okay, and so in that way, our final answer here has to be, that would be 1/2 right there. And actually, I mean 1/4. My bad for the little bit of miscalculation. Okay, and so much limit work, but I need to remind anyone again, our goal here was to find, so this final answer we have found right here is our final derivative. It's our capital H prime at 4. It's the derivative value of our function capital H at x equals 4. And so making that final conclusion, and the answer is still there from that from part of that other board right there. So our final answer here, capital H prime at 4 as a final conclusion. Our function's name is capital H, and I apologize for, earlier when I was writing down the problem, I mistakenly used h without realizing that we already used h for that. It might cause some misunderstanding, so I switched to capital H. Forgive me on that. That answer there equals 1/4. Okay, but once again, remind yourself, the entire purpose of doing any derivative work is that the derivative work is to represent the slope of the tangent line. So here's our function. It gives you whatever graph that is, but when x equals 4, we have the slope of the tangent line there equals 1/4. Okay? And so, once again, I am going to create part B, but my purpose, my intention here is for viewers who has been following along with my video lecture here to have a second opportunity to work independently on your own. We're going to focus on the same function. Okay, so give me some time to erase the board. All right, so let's look at part B. Let's evaluate capital H prime at 9. Okay, and so now, as I already mentioned about my plan for these problem part B right here, it's meant to be an FYT for you viewers to try right here. Okay, and I can help pointing out the starting setup right here. And by the way, I keep having my student mistaken my handwriting here. It's just a handwriting thing that I can't get out of it, but this is my 9, by the way. And my G looks like this, okay? My lowercase letter G looks like this. So you can view that closely right here. I was raised in a scripture writing tradition right there. So h prime of 9, we can set it up by that famous difference quotient. H, our a value is 9, so h at 9 plus little h, okay, minus h at 9, and dividing that by h here, and we want to take the limits as h goes to 0. Okay, and so I'm going to take a pause right there. I'm going to take a break. I'm leaving that for any viewers, for any one of you who views this video to continue with your steps right there. All right, and I'll be waiting for the final answer. All right, and hopefully anyone after pausing the video and made your own steps right here, and now let's resume the video. My answer here hopefully agrees with yours. My answer here is 1/6. Okay, that's my final answer after a bunch of steps in writing down the actual limits problem and reducing it and getting through the steps right here. So now ultimately we're saying that h prime at 9 equals 1/6. That is our final answer. We can put it in a box. And this once again represents if our function h of x here has some kind of graph, then at x equals 9, the slope of the tangent line here equals 1/6. Okay, and I keep changing my words in terms of how I explain, but in the end it's all about the slope of the tangent line. Okay. All right. So once again, but this time I believe anyone who has been following with my video has hopefully fluent enough with as far as the amount of steps and what you need to do when you're finding a derivative, any derivative. So, and remind yourself again, the derivative is to represent the slope of the tangent line at the specific given point. Okay. So I feel like I owe anyone viewing the video one big favor, and let me point out that favor in the following example. And at this point, after this last example here, we can be done for this particular lecture over here. Let's call that now example 5. Okay, and so now give me some time to write it down. It's going to be a lengthy problem. Let's find the equation of the tangent line. Find the equation of the tangent line to the curve of our function here is f of x equals x squared, okay, at x equals 1. Okay, so it's one statement, but it has a lot of things to go. So in this example 5, our example 5 is asking find the equation. If you now can pause maybe the video or rewind that and roll it back all the way to the beginning of our lecture here when we first started looking into the derivative, where I first promoted the idea about finding the tangent line. We only stopped at finding the slope of the tangent line, but we never completed the equation of the tangent line. So as a matter of fact, back in our promoting problem, then we already found the slope of that tangent line right there, because if you can realize this is all the same information. So now I need to remind tangent line or secant line or whatever line famously in that form, slope mx plus b, the slope times x plus the y coefficient, the y intercept. I put that little subscript t right here to indicate that this line is a little bit special. It's just a tangent line, okay? And so, and what I said earlier about this function has been used in my promoting problems way at the beginning when we first started talking about derivative. Then it's all in the purpose of making it easier for viewer, and we don't have to reinvent the entire wheel from scratch. So here, this line right here, we already found for this particular tangent line at x equals 1, our function here is x squared function, and at x equals 1. So immediately after I write this next information down, go ahead and pause the video after I write this down and roll it back to the earlier part of the lecture to convince yourself that we already had this answer. Okay, but our slope of the tangent line here on this particular function is 2. Okay, we already found it. We already found in the very earlier part of the lecture. Go ahead and pause the video, roll it back to that point right there, and find it. It's all the same exact function at the same given point that we've had. Okay. And now, hopefully, you already rewind your video and looked at the result we've had. Now, this problem here in example 5 wants us to step further. We want to step forward and find the remaining missing information. Okay, so that 2 we have found previously is only the slope of our tangent line equation, but any line equation must be in the complete form slope times the input variable plus the y-intercept. Okay, and so we were only halfway, but that first half is always the more dominant, the more important ones. How's that? So let me switch to the other board, and I'm going to need to erase all this work here, and let's find out. And so now, at least knowing that our slope of this tangent line has already been 2 for here, then we can partly see that our equation of the tangent line at the end would need to be, so y equals, it needs to be 2x, but plus with some value. So we're about halfway completed with our tangent line. Okay, and so the remaining part here is just to find out what value that is, but what value for the y-intercept that is. So at this point, you have your own flexibility, because anyone viewing this video, you are expected to be at the calculus level. So there's no reason to show you the ultra basic stuff from algebra. You can just 2 options, but we need one thing before I point out the 2 options here. Back to the famous graph of your x squared function. X equals 1 is right here, but that is on the x-axis. The tangent must be placed. The tangent is not on the x-axis. The tangent is on the graph. And so that point right there, and I also introduced that in our very beginning of the lecture over here, that this point here is now, let's give it a name, tangent point. So the tangent point is important because so the tangent point here, I am going to substitute. Okay, so for the tangent point, even though I already introduced that, but famously tangent point is always from where the value we gave. So x equals 1. Right? We're going to substitute the y value, which is f at 1, and f at 1 in our function being f of x equals x squared. So our function being f of x equals x squared, so f of 1 has to be just 1 comma 1. So that's why here's our tangent point. Okay? So a little bit of explanation for anyone in case you felt shocked how I got that. But now, the whole reason I mentioned tangent point is because your tangent line, it makes sense that way. This point is called a tangent point. The tangent line is placed right at that tangent point. Okay? And so now, if we can complete our equation and we already halfway done, we got the slope. Once we can get that y-intercept value right there, and we're done, and we can accurately put our tangent line in the hand sketch version here. Okay, and so now after we found the tangent point, then what can we do here? We can treat the tangent point, because now we don't even need the graph of the actual function anymore, but our line right here. suppose we already know the slope. We already knew the slope, and we know there's a point given, 1.1, 1 comma 1 being on the line right here. Then we've got a couple options. Option number 1, we can go with the equation currently being 2x plus b. Okay, option number 1. We can substitute the same equation, but if this point is meant to be, the tangent point is meant to be on the graph, then it's meant to be on the line. I should have said that. Then the y value and the x value must be substituted into the equation and be satisfied. Or in other words, we can substitute y for y and x for x. Okay, that's one trick right here. And from here we can solve for the b value, and we can quickly solve for b. So b here is -1. That's one way, quite standard. We tackle right down from the slope-intercept form, which is halfway completed, and then we substitute that point. This tangent point is supposed to be contained on the line itself, on the tangent line itself. Now another option, if you can also still remember. So the more options you remember at this point, the better it is, the more flexible your work can be. But like I said again, same ultimate goal. We already knew that our slope is 2. Okay, and we know that our tangent line, and I even put the graph, the actual graph of the function away. I only want to demonstrate the idea that we already knew the slope, and we know that the line that has the slope must also contain that given point. So how do we get the complete equation? Another option here, and I call it option 2, is to use they call the point slope equation. So the point slope equation here is we're going to start out with saying, hey, y, the variable of the equation, minus 1. 1 is the y value of the point being on the line. So y minus 1 equals slope 2 times the x variable of your line equation minus 1. Where did that other 1 come from? That other 1 came out from the given x equals 1 value. So this is the y value of your tangent point. This is the x value of your tangent point. This equation here, as a reminder, is being referred to as the point slope equation. So with the point slope equation, now we can also put that equation back to that famous form right here. So I can minus 1, I can multiply 2 or distribute 2 into each term here and getting a 2x minus 2, and now I can bring that add that 1 to the other side. So now we are ready. So either way, so here I'm going to be arriving at, if I went with point slope form, then I'm going to end up, after adding that 1 to both sides, my final tangent line equation is 2x minus 1. Okay. Same way here, if I already started out with using the direct slope-intercept form of my tangent line, I personally favor this, but that doesn't mean viewer have to go with what I favor. Okay, getting the equation of the tangent line is what we need. So once we found our slope, our y-intercept being -1, then once again completing the equation of tangent line. Our tangent line is 2x minus 1. Either way gives you the same exact answer. Either way gives you the exact same answer. Okay, and so now our final equation here is y equals 2x minus 1. Okay, so we found the equation of the tangent line. All right. And so now, after finishing with example 5, there are some other details that I really want to mention for here. So as far as, now, before I mention these details here, anyone must understand that finding the equation of any tangent line is such a big work in throughout our entire quarter learning calculus. And so believe me on this, at any point, no matter how far you have gone into your calculus quarters, at some point there will be a problem again that asks you the exact same thing. Find the equation of the tangent line, tangent to the whatever function here at a given specific point. Okay, so let's, at the end, even though we already finished with this example 5, but allow me to point out a couple of highlighted steps that sort of quite standard, so that anytime you are being asked to find the equation of a tangent line, doesn't have to be the same function here anymore, doesn't have to be at that specific given point, but let me now point out a couple of steps right here. And those standard steps, they have a certain order right here. So first thing, know that your tangent line has to always be in that form. Y equals mt slope mx plus b. Okay? And then the big step 2 right here is there to find slope. It makes sense that way, that our equation here involves slope and y-intercept. So first thing we have to do, find slope, and I refer to that as step 2, quite standard. Now the reason in my example 5 the step 2 was so short because we have already found our slope previously in the earlier part of the lecture. So here I'm just reusing it. But in reality, in practice, when you are thrown into a brand new function, then we have to restart all that. And so remind yourself right here. So this slope right here really came out from, this slope right here really is the same as, shouldn't say arrow, but should have said, this slope value, right, is equals to the function, taking the derivative of the function at the given value, x equals 1. So this is the big word right here. So in case you are being given with a different function, a function other than the one we already worked in our example 5, this is what you need to do right here. Okay, so that's a big standard step right here. And the next big step, I had to erase that in my earlier board right there. But the next big step is to find out where your tangent point is. So get your tangent point, because we have to know where the tangent line is being placed. And so the tangent point is always at that specific value a that's given in the problem. And then the y value for that is your function at a. This is famously your tangent point. And so now in the next step right there, after tangent point, the next standard step is to be able to complete. So this step right here, sort of like step 4, I went with 2 options to remind you about your own algebra skills, and you got different options to approach. But step 4 right here is sort of like the last step to complete the equation. And completing the equation, it really intended that we are finding the missing coefficient. So that step right there, once we find that y-intercepts, we complete our equation. And so finding the y-intercepts, you got 2 different options. Options 1, we can go directly with the halfway found, halfway completed equation and just plug in the tangent point value. See, x for x, y for y, and solve for b. Okay, and then complete your equation. Option 2, with the tangent point that you already found in step 3 right there, we can just directly use the point slope equation right here and then rearrange the equation to arrive finally at our complete form mx plus b again for your tangent line. Okay.